Okay, lecture 23. So we'll continue the discussion of LPMLN language. I'm going to show you some examples and also tell you about some system that compute this language. Okay. So as you saw last time, the idea of LPMLN was to combine the advantages of both ASP and Markov logic. So let's recall what was the semantics of LPMLN. We start with, by the way, syntax is simple, so it's a weighted answer set rules. And we define this auxiliary notion pi subscript I, which is not to be confused with the reduct. This is actually simpler than the reduct in the sense that you just collect the rules that are true under the interpretation I. Okay? And when you find an unnormalized weight, this is in two cases. So given an interpretation, you can find what are the subset of the rules that are true under that interpretation. So look at that subset and ignore all the other rules that are not true. Now, within this subset that are true under the interpretation, if I is a stable model of the subset, then we do the same thing as in Markov logic. So collect those weight, add them all the weight of that satisfied rules, and make an explanation. And that's one part. But now it happens to be the case that I is not a stable model of that subset that you talked. Then the weight gets a 0. So this is actually what distinguishes this from Markov logic. Okay. So just in case, if you actually forget about the stable model, you say that I is a stable, I is a model of unweighted subset, then this case does not arise. Okay. So then this definition reduces to a Markov logic definition. Okay, so the difference between Markov logic and LPMLN semantics is about requiring this subset to generate a stable model. Otherwise, you assign the weight 0. Okay. Okay. Okay, so that's how you actually compare the semantics with Markov logic. All right, once you have that, normalized weight, also called probability, is just this, okay? You just add up all the weights of all interpretations, and that's the normalization factor. So we talked about this example before. So for each of the interpretations, you have to find which are the subsets of the rules that are true. And this subset can be different among, depending on which interpretation that you choose. And after that, you can get the weight from each of the rules. Now, note here that sometimes you have non-zero weight, but if this is the case, in this case, it's actually not a stable model. This interpretation is not a stable model of these rules. Then the weight gets 0, so that the probability is also 0. Okay. So this is what you can do. Okay. And when you have the probability questions, this is actually same as the basic notion of probability. So how do we know that what is the probability of bird of Joe is true? Then you go all the interpretations that satisfies the formula bird of Joe. So for instance, for this query, okay, bird of Joe is satisfied by these interpretations. Okay. 1, 2, actually 3, 4. Okay, so there are 4 interpretations that makes bird of Joe to be true, and you collect all the probability, you add up all the probability, that becomes 1. And for the conditional query, this is also the same. You have the probability of bird of Joe and resident bird of Joe divided by the probability of the resident bird of Joe. Okay, so that's how you do the conditional probability. There is actually nothing different from the basic probability theory here. Okay. Now note here that when we use alpha, our intuition is to make each of the rule hard, which makes definite knowledge. So everything has to be true. But if you go into different ways, like 2 and 1, this is not alpha, so it's not an infinite weight that we capture. So it's kind of certainty factor with different degree. So if you do that, you will get some different probability. Okay, but the probability computation is actually the same as before. Once you have this, you can normalize with respect to same idea and same computation. Okay. All right. So what alpha makes a difference is we make alpha to go infinity when you compute the probability. So if you have more alpha to be satisfied, that interpretation dominates the other interpretation that satisfies less alpha, and that those other interpretation becomes actually 0 in terms of probability. Okay. So. All right, so now let's look at some examples of LPMLN language and how that can be useful. So here we want to talk about the path problem. And we did these problems in ASP. We had Hamiltonian cycle problem or coloring or clique. There's a lot of different graph problems that we did in ASP. Now, you can actually easily extend every problem there in terms of the probabilistic setting. So you can actually assign probabilistic uncertainty there. So for instance, suppose you have a graph and actually you don't know what is actually the graph there. Okay, so you don't know whether the edges are present or not, but you know that there is a certain path between them. Okay, so for instance, if you think about some network connectivity, you know that from this node to another node there is a connection, but you don't know what is actually the path that they are following. Okay, so you can actually find out using this probabilistic LPMLN language. Also, you can say that given the two nodes with certain probability of the edges, what is actually the probability that a path exists between them. Okay, we are going to see some more specific examples, but for now, this is the kind of query that you want to do in terms of probabilistic setting. Okay, knowing that you can describe graph in terms of ASP problems, the only thing that you need to add is actually probabilistic information. Okay, now how we do that in terms of these paths, we don't know whether the edge is there or not. Okay, so edge has the probability, okay, to be true or false. Okay, so for this kind of thing, what we are going to do is just add this fact that when you describe edge relation, so let's say there's an edge between 0 and 0 with 30% chance. What you do before was just to write edge of 0, 0, meaning that there is a self loop there, right? And that's definitely true. But now you want to make it uncertain. How do you do that? You put the log of 0.3 over 0.7. And we actually talk about why this particular number before. Do you remember this part, right? I don't have to repeat. Okay, so if you want to say this is 30% chance that this atom can be true, then you can encode log of 0.3 over 0.7. Okay. Similarly, you can do with the edges. Now edge 0, 1, or 0 and 1 are connected by an edge with 20% chance. Okay. So this is actually what you need to do in terms of saying the edges. But other than that, the path relation is just the same ASP rules that you have written before. So it's a recursive definition. So edge, if edge is true, then that makes a path to be existing between x and y. And path of x to y, there is a path between x and y. If there's a path between x and z to y, and say y is different from z. Actually, this last is not essential, but sometimes it helps to search. Okay, are we together? Okay, so just take most of the ASP encoding, actually, all we did in class in terms of this graph problem. The graph was represented by a set of nodes and the set of edges. And you can always turn the edges into a probabilistic fact. Okay, all right. And you can easily do the probabilistic trail length salesman problem. So we had this Hamiltonian circuit problem, right? And we had also, there we have how do we find the Hamiltonian circuit from the graph. Now you can actually say, well, these nodes are not necessarily connected. There is a certain chance that there's a edge between them or not. You can make it as a probabilistic version, which is typically more difficult than the deterministic version. But you can easily solve it using the system for computing LPMLN. Okay? All you need to do is just to change the edge relation to be probabilistic. Okay? Other rules are actually the same. And there is also interesting thing. I don't have slide here, but you can easily imagine when we do the traveling salesman problem, there was a cost function. So each edge was represented. Each edge is associated with the cost, and we want to find optimal plan, right? And this optimization of the cost and this probability is kind of orthogonal things. So you can actually make a so-called decision theoretic version of this problem. So you want to say, you want to find the Hamiltonian circuit with, let's say, 50% of chance that exists, but the cost is optimal. Okay, so you can actually create the combination of these problems. Okay. All right, so let's actually look at a specific example here, just to illustrate this idea. This is a bit different from the previous slide in the sense that now what I'm going to do is to turn the node to be probabilistic. But you can imagine a similar idea here. Okay, so there are four nodes here. So 1, 2, 3, 4, and they are connected by this graph. Okay, as in this graph. And for node 1, we want to send out the signal. And each of these nodes, you can think about as a certain station that receive the signal and forward the signal. But each node has certain failure. Okay, so node 2 can fail with 80% chance, and node 3 can fail with 50% chance, and node 4 can fail with 20% chance. Okay, and the graph is actually shown here. Okay, now how do we represent connectivity? Well, same as before, x and y is connected if there's an edge between them, but now we want to say if each of nodes are not failing. If each of nodes does not fail, then these nodes are connected. Okay, and of course x and y are connected if by transitive closure, if x is connected to z and z is connected to y. Okay, so let's think about it. What is according to this description, we are going to actually run the system to check this, but according to this thing, what is the probability of edge 1 and 2 to be connected? 20%. That's actually given here, right? Okay. 80% is the chance for the fail. Okay. Actually, yeah. Okay. Good. How about node 2 and 4? Two and 4. Somebody says 16%. Is it? Yeah. Because both of them has to be not failing, and that's the chance of the here. This is actually success rate. So 0.2 times 0.8 is 0.16. 16% of chance that node 2 and 4 are connected. Now the real question: what is the probability that 1 and 4 are connected? And that is something that we want to do with Socrative. Okay. So this time I actually gave a multi-choice, so we can just go. Okay. So think about it. You can discuss with your peers if you want. Okay. Who needs more time? Okay. Let me give you 1 more minute. So. Okay, let's see how we did. Okay, quite diverse. Somebody really chose E here. Okay. All right, so 45% A, but B and D are also kind of close. Okay, so let's actually look at this together. All right, so node 1 is always successful, so there is no fail on this. So we can just enumerate the possibility of each node to be failing. So now we have to still connect it. So if node 2 is, let's say, false, okay, then in order to be connected, 3 and 4 must be connected, right? So this is one possibility when node 2 is false. So node 2 fail, actually. I should say, let's actually use fail, okay? So this is fail, successful, successful. If node 2 fails, then the only way to connect it is through 3. And 4 must be also successful, okay? Now, when node 2 is actually true, successful, or not failing, okay? What about the case? Well, in that case, actually, we don't need to rely on node 3. We can actually directly go from node 2 to node 4, assuming that node 4 is actually successful. In fact, actually, for all cases, node 4 must be successful. Here, node 3 can actually fail. Okay? But also, node 3 can also be successful. There actually is only 3 possibilities. And you just need to compute the probability and add up. Okay? So what is the probability that you get node 2 fail and 3 and 4 successful? That's 0.8 because that's the failure rate. And success is, now look at this one, so 0.5 times 0.8. Okay? And for the second case, node 2 should be success, so that should be 0.2, and then fail, that's actually 0.5, and same as before, 0.8. Okay? And everything successful, that's a 0.2, 0.5, also 0.8. Actually, the third is actually 50-50, so it does not differentiate. So if you compute everything here, that is actually, this is, the first one is 0.32, the second is 0.08, the third is 0.08. So the correct answer is A. Okay? I'm sorry, no. This is not. What did I say? Actually, I got wrong here, right? 1, 6. I should have 0.48, right? Yeah, I think I did calculation error here. So the correct answer should be 0.48. Sorry about that. So actually E was right. It was not my intention. Okay? So sorry for the confusion, but looks like E 0.48 is correct. Okay, good. Okay, so then let's actually check this. This is actually the system that you can use. We are going to talk about this system in a moment. When you run the program, you will actually get this output. And in fact, as I just said, 0.414 is actually this one, so 48%. So I don't know why I didn't copy the right one, but this is the answer. Okay. Now, as you see, even for this simple problem, there are a lot of different cases that you have to consider, right? So in ASP, the strength there was you can actually enumerate all possibilities. But the limitation was all the possibilities were treated equal. But in many cases, like this example, the possibilities are not equal. Sometimes just something is more possible or more probable. So by doing LPMLN way, we can actually differentiate between those possibilities and we can get the probability. Now, if you actually try to feed something like this into alchemy, okay? So syntax is a bit different, but basically you treat this rule as a formula. So if the body is true, then it implies the head. Okay, you can encode this in alchemy. And if you do that, this is actually what you will get as output. Okay? Now something is actually unintuitive because here we don't actually have, according to this recursive rule, we cannot actually connect 1 to 1, for instance, because there is no edge from 1 to 1. Okay, so connected 1 to 1, 1 cannot be actually be derived from the program. But according to the alchemy, the head can be always either true or false. Actually, the body doesn't necessarily have to be true to make head to be true, right? Because implication is true when body is false or head is true. Okay, and because of that, you will actually get these many possibilities, and in fact, connection between 1, 4 is actually 36%, which is actually not correct. Okay, so this is how you get. The point is, the alchemy is based, MLN, Markov logic, is based on first order logic. And the first order logic is known to be unable to capture the notion of transitive closure. Okay, so there's actually a well-known result. First order logic cannot capture the transitive closure. If you want to capture it, you have to go to the second order logic. Okay. Okay, so that's actually the limitation of the Markov logic for reasoning about transitive closure or reachability or connectivity problems. Okay, next. We also know that answer set programming can be used for the planning. Okay, we have formalized some Bloxwald domain and monkey and bananas. One thing that I used to give an assignment was actually the wolf, sheep, cabbage problem. It's similar to the problem of missionaries and cannibals. You can actually encode this in ASP, but here let's consider a variant of the problem. So the original problem is saying that if wolf is left with sheep without the farmer, then wolf will eat the sheep. And similarly, the sheep will eat cabbage if farmer is not around. Okay, but now let's assume that sometimes wolf does not always eat sheep because maybe he's not hungry. Okay, so what you can do is you can formalize this domain as a deterministic ASP. Okay, so for instance here you can say about the effects of the action. Okay, so if something is on the board and location, it's actually indirect. Is a state constraint. If something is on the board and board is at one location, then that object is at the same location. This is inertia rule that you saw before. Usually the things will stay in the same location, and this is an action. If the object get on the board, then on board will be true in the next time. If you move the board to the destination, the board destination will be at that destination. Okay. Now here we have the things that wolf and sheep, but the boat is not there, meaning that the farmer is not there. Then sheep will be eaten. Okay. But we actually do write this as a soft rule with weight that is different from alpha. That means sometimes this can be actually violated. Okay. So there are some other rules that I think I skipped, but you can say in the maximum max step. in the next step, wolf and sheep and cabbage should be all in the destination L2, and sheep should not be eaten. Okay, this is what we call success, and we want to find the plan that is successful. Now, original problem actually takes 17 actions of crossing. Okay, you can try if you want. Okay, this is similar to the mission and carnival puzzle that we did. But with this elaboration, you can actually get 11-step solution where the wolf does not actually eat sheep. But this is actually less probable than the deterministic plan. Right? So if you want to be risky, you can get shorter step solution. Okay? All right, so this is it. Okay, let's go back to the smoker example. It's actually the slightly different version of smoker example. And here is another Socratic question that we are going to do. Let me first explain the domain here. So forget about cancer and forget about friendship. Okay. So here instead of that we have influence relation. Okay. So if X is a smoker and if X influence Y, then Y smokes. Okay. All right. So this is actually a soft rule. This W represents non-alpha weight. It can be some real number. Okay. Now there are alpha rules which we know for sure. We know for sure that Alice is a smoker, and we know for sure that Alice influenced Bob, and Bob influenced Carol, but nobody else influenced nobody else. In other words, these are the only true relations in influence, and all other pairs doesn't satisfy the influence relation. Given this, easily we can see that with this Markov logic network, the probability of the smoke of Alice is 1, because this is actually the hard rule. You can easily compute this one. What we are interested in is, we know that Alice is smoker, but we don't know whether Bob and Carol are smokers. But we know Alice influenced Bob and Bob influenced Carol. Okay, so what is actually true about their probability of being smokers? So that's what I'm going to ask you now. Again, this is multi-choice, but there is no D and E. Okay, so think about this. If you have done the homework, and if you understand the Markov logic semantics, that should be enough to answer this question. If you don't have any idea, just have a random guess. Now I should actually say W is a positive number, otherwise it may be opposite. Okay, do you need more time? No? Okay, so let's see. Okay, majority is saying A. And some people say C. Okay, the answer is, of course, C. If it was A, I would not have asked you that question, right? Okay, but why? This is tricky. So intuitively, A makes sense because A is closer to Bob is closer to Ellie, so that her influence may be stronger than Bob influenced Carol, right? So that's actually what you intuitively expect. But what happens is actually not, according to the MLN semantics. So this is actually where you actually have to relate the difference between first order logic semantics and the stable model semantics. Okay, so all these things are actually connected. What you learned in the semester is actually coming up again here. So what we know for sure for this domain is smoke of A must be true, because this is actually the hard rule here. And influence A and B is true, and influence Bob Carroll is true, but other influence relations are all false. So the key part is actually this rule. This is the soft rule. And since we have three objects here, three persons here, this rule will generate 9 possibilities. So 3 for X, 3 for Y. Okay? So if you ground this first rule, you will get 9 ground rules. Are we together? Okay. Among these 9 ground rules, some rules are obviously true. Okay? So which rules are obviously true? What are the obviously true rules? The first one, is it true? Yes. Why? Influence A, is false. The antecedent is false, the whole thing is true. The second one, we are not sure yet, because it depends on B is a smoker or not. Okay, so let's skip that for now. Third one. It's also true, same reason, influence AC is false, because that's what we said here. All other values, pairs of XY, influence is false. So this is false, okay. Antecedent being false means that implication is true. So these are true. And this one we don't know for sure yet, so let's skip. But the other things here are all true. So among these 9 rules, what matters could be these 2 rules. Okay. So since influence relations have fixed interpretation, let's actually look at the smoke possibility. So we want to say possible world. Okay. So here, what are the possible worlds? So influence relation is fixed, and smoke is actually fixed for the Alice. Alice is known to be a smoker, right? Okay. How many other possibilities are there then? 4. Because depending on whether B and C are smokers or not. So there are 4 possibilities. So for all 4 possibilities, Alice is a smoker, but Bob is not a smoker and Carol is not a smoker, right? So this is one possibility. And Bob is a smoker and Carol is not a smoker. Okay, so Bob is not a smoker and Carol is a smoker, and all of them are smoker. Okay, are we together? All right, so now let's talk about the weight of this interpretation. Okay, so there are I1, I2, I3, I4. There are 4 interpretations. Let's look at the last one because that's probably simple. What is the weight of this last interpretation? What? What is the weight of this interpretation? We are looking at Markov logic. Okay. E to the power of 9W times e to the power of k alpha, because alpha rules are all there. But let's forget about alpha rules. Okay, so let's only look at this one because all the interpretation will satisfy the same set of hard rules. So it will cancel out when you do the probability. Okay, so let's actually look at only the weight coming from the ground rules here. The last interpretation satisfies all of them. Okay, so 9W is the sum of the weight, so the weight is e to the power of 9W, right? Are we together? Good. Now let's actually look at the first one. So A is a smoker, and B is not a smoker, and C is not a smoker. The only two rules that we are not sure is actually the second one, and I think it was 6th rule, okay? The second one, is it true under the first interpretation? It is false because smoke A is true, but smoke B is false. So this is true, but this is false. So true implies false is false, right? So this rule is not satisfied by the first interpretation. Are we together? What about the 6th rule? The 6th rule is about smoke B implies smoke C, but also smoke B is already false, so the antecedent is false, the whole thing is true. So what is the weight of the 8W? Okay, the only one that is not satisfied is actually this one, okay, the second one. Good. What about the next one?
Same way. 6th rule is.
So now the second rule is actually true because smoke A and smoke B, both of them are true. But if you look at the 6th rule, smoke B is true, but smoke C is false. So the formula, the 6th formula is false. So the weight is, yeah, good. What about the next one? So this is the same as the first case, right? So smoke A is true, but smoke B is false. It does not satisfy the second formula, but all other formulas are true. So you get actually e to the power of W. Okay. Knowing this, let's go back to the probability of Bob being a smoker. What is the probability? Now look at this table. Okay, can you say what is the probability of the Bob being a smoker? Which interpretations make Bob to be a smoker? Second and fourth, right? So from these we get e to the power of 8W plus the second one, okay, e to the power of 8W. The last one, e to the power of 9W. And the normalization factor here is the sum of all the weight here, so that's 3 times e to the power of 8W plus e to the power of 9W. Okay, are we together? Good. What about the probability of Carol being a smoker? So we have to, the denominator is also the same, so that's whole sum. I don't need to worry about that. Now I have to look into the case that Carol is a smoker. Which interpretations make Carol to be a smoker? Third and fourth. So what do you get as the numerator? E to the power of 8W and e to the power of 9W. And what do you get? They are same. Okay, that's what Markov logic tells you. The reason for that is obviously because of the semantics of implication. Okay. So the next question is, actually this is actually the typed example. You can compare it. Now let's actually go back to the LPMLN. So in the case of LPMLN, what I can say is I don't need to say for all other pairs of x and y, they are not they don't have influence relation. I don't need to say that because by definition, the stable model minimizes this extent. So if I don't show this, then for all the other pairs of x and y, influence relation is false. So that part I can save. But other than that, I'm trying to capture the same thing. So what is actually now the probability? And here you will see that the answer is actually A. And let's actually check why. So doing the same example and doing the same computation. Okay. So again, this idea is coming from the first rule. It generates 9 ground rules. Okay. So we'll actually do this together. Okay. So possible world. So one is A is a smoker, but B and C are not smokers. Same thing as before. Okay? This is possible word. And we want to have the weight. Okay? Now, for each interpretation, again, same as before, we know some rules are definitely true or false. So let's actually check that again. So which rules are definitely true? So this one is true. This one is true. This one is true, true, and true, 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 right? Again, so the second one and the sixth ones are not known yet, okay? Let's actually look at the last one, okay? So, what do we do in the LPMLN? So if you apply the last interpretation, we have to find all rules that are satisfied, right? Actually, all rules are satisfied. Okay. Now, but we have to check whether this one is a stable model from the coming from this subprogram, right? Which is the whole rules. So, is this one a stable model of the subset?
Yes.
Okay. Yes, it is, because we know smoke A is actually true. And if smoke A is true, then this one makes smoke B to be true. And if smoke B is true, then this one makes smoke C to be true. So this is actually the minimal model that satisfies all of them, right? Okay, so here let's ignore all the hard rules weight, but same as before, we'll get e to the power of 9w. Good. Now let's go to the first one. So this time it's actually the same subset that we are looking at, right? So I don't remember what was that. I guess the second rule was only the thing that is false, right?
Yes.
If you apply the first interpretation. Okay. Now, so ignore the first one for now. Okay. Now let's check whether this interpretation is a stable model of the 8 rules. Is it?
Yes.
Okay. So smoke A definitely is true because of this one, and smoke B doesn't have to be true, and in fact, none of the rules actually can derive smoke B, right? And smoke C is also doesn't need to be derived. So in other words, smoke A is the minimal model of this program, right? There is actually no negation, so you don't have to consider the reduct. We just need to find the minimal model. Are we together? In the case of ASP, we actually use this notation better, more than this way, but you can identify. Okay? So SA is the minimal model of this program. So what is then the weight now?
8w.
Yes, the weight is actually same as before. Good. What about the next one? So smoke A plus smoke B is false, smoke C is true.
Not a minimal model.
Okay, so let's first look at what subsets that we have to look at, right? Okay, so what are the rules? Let me actually erase the part. Okay, so these are all true. So which rules are false under the second interpretation?
Rule 6.
Rule 2 or rule 6?
Rule 2.
Rule 2 is false, right? So this is actually the same thing as before. And, okay. So then, is this, so we found this subset. Is this a stable model? The second interpretation, is it a stable model of the rules?
No.
Why not?
We already found SA. We already found SA is the stable model. Minimal model.
Yes, that's actually one way to say. The difference here is whether we are asking for the same program, whether this is a minimal model, but this is not, okay? We already found that SA is actually the minimal model. Another way to say is smoke of C doesn't have to be true, right? Because only rules that make smoke C to be true is are these rules, but their antecedent is false. So you don't have to generate smoke of C. So the minimal model is just smoke of A, which is different from this interpretation, the second interpretation. Okay, in that case, what do you assign for the weight? 0. Okay, question here? Yes?
Could you go over why SA was the minimal model earlier?
The first one?
First one, yeah.
Okay, the first one was actually looking at the same rules, so just forget about this, okay? And you try to use, so smoke A, does it satisfy these rules? Okay, so first, one thing that I have to clarify is I actually omit all the discussion about inference relation because that has fixed interpretation. Okay, so when I say smoke A, I actually mean smoke A union with all the true influence relation. Okay, so if smoke A, whether smoke A is actually the minimal one together with the fixed influence, yeah, because smoke A is true here, and if smoke A is true, that's actually you already have that. But other smoke B and smoke C doesn't have to be derived, right? Are we together there?
Would we be getting smoke of B because of the first rule?
Smoke of B this has smoke A in the head. So the first 3 rules cannot be used to derive smoke B, right? The only rule that can, the only rules actually can derive smoke B is this one, or this one, right? But we know that this is already false. We forget about it. This is not a subset that we have to look at. And this one, the antecedent is false, so we don't have to derive smoke B. Same for this guy. Okay?
What about the second rule?
Second rule was not satisfied. So when we check, remember we are only looking at the subset. So first step is we ignore the rules that are false, and then using the remaining rules to check whether the I is a stable model of that remaining program. Okay, so that's what you get. Okay, so I think the idea is clear. If you got confused, it's not really complicated things. You can actually go back and compute by yourself. Let me know if you have difficulty in doing that. The last one is actually similar. You will actually get e to the power of 8w. Okay? So then let's actually think about the probability of Bob being a smoker. What is the probability? Note here that one of the interpretation now gets weight 0. So the normalization factor is 2 times e to the power of 8w plus e to the 9w. And what is the probability of Bob to be a smoker? That's actually the third and last one. So e to the power of 8w plus e to the power of 9w. Good. What about Carol to be a smoker? So that has the same denominator. And what about the case that C is a smoker? It's actually only 1 now. Actually 2, but 1 is having the weight 0. So this one is e to the power of 9w. So which one is bigger? The first one. So this is bigger than this. Okay? Now why this happens? In the case of stable model semantics, note here that this does not make sense. Okay? Because we know that smoker is a chain relation. If A is a smoker, then B is a smoker. If B is not a smoker, then you actually get the penalty because you don't satisfy some rules. But there is no way that Carol can be a smoker without Bob to be a smoker. This is not possible because there is no cause for Carol to be a smoker. That interpretation is unlikely to happen. So that's why the weight is 0 there. Okay, and if you do that, then the probability actually makes sense. Okay. All right. So I think this was kind of heavy in the computation, but let me actually entertain with some other things now. Let's actually talk about the system that you can play with. Okay. So there are 2 versions of the system, 2 different implementations of LPMLN, which you can download from this link. The first one is to use Klingo as an engine for LPMLN. The second one is using Alchemy as an engine for LPMLN. Actually, we also support other Markov logic network implementation, which is Tufi and Rocket. Okay? So there are actually options that you can call with LPMLN to MLN. Okay, so probably next class we are going to talk about the underlying algorithm for this system, how you can translate LPMLN to ASP and MLN and so on. But today we'll see how to use this system. So the first version, LPMLN to ASP. The input language, by the way, these two systems have slightly different input language because their target language is either ASP, Klingo, or Markov logic network implementation. So the syntax, slight difference in syntax coming from those target implementation. So first implementation is LPMLN to ASP. So the input language is actually very close to Klingo. In fact, what you will see that the only difference is you can actually assign the weight. You can prepend the weight in front of the Klingo rules. Okay. Otherwise, these are actually the same. So soft rules are Klingo rules with the weight prepended, and every rule must end with period. This is slightly different from alchemy. In alchemy, if you have a period with no weight, that's a hard rule. If you have no period with the weight, that's a soft rule. Okay, but here every rule must end with period because that's what Klingo requests you to do. Okay, so here's an example, the bird example that you saw, and the only thing that is different from the Klingo rules that you saw before is actually you can assign the weight. If you don't assign the weight, then we assume that this is hard rules with infinite weight. The rule is alpha. Okay, if you want to know more about the command line option, then there's a help file or help option that you can see all the options of the system. But I'm going to show you how to run this system. So here is the program. The same program as ASC. The input command line is very similar to alchemy. So you specify the input file, which is bird.lpmln, and you specify the -r output file, and -e is the database fact here or evidence. Here this is actually empty, but you can also query the predicate. Okay, so predicate with no argument. That's actually how you call alchemy too. Okay, so if you type this, then you will get this output. Okay. I think it's clear, so let me not just type in these things. Let's go to the next one. So this is actually the example that you can see. One of the questions that we talked before was, what is the probability of Joe being a bird if you know that Joe is a resident bird? Okay, so how do you specify this condition? The condition can be represented in the evidence file. So now you use the non-empty fact. Here, you have to have a double negation, which means actually the positive. So one restriction is whatever that you put in the database fact must be a constraint. Okay, not the positive rules, but always have to start with this dash colon dash. Okay, so this dash arrow not means that resident bird must be true. So knowing that resident bird must be true, what is the probability of Joe being a bird? So the difference now is you specify this condition in the evidence file and you query on the bird, and then you will get this probability. Okay, all right. If you do the opposite way, if you happen to know that Joe is a bird, then what is the probability that Joe is a resident bird? Okay, this is not necessarily 1 because Joe might be a migratory bird too. So if you do that way, you will get 73% of chance that Joe is a resident bird. Yes?
So when the LPMLN is parsing this, is there any difference between that line being in the original LPMLN file versus provided separately? Will it still be parsed if I decide just to run that line of code minus the E bird N2, but instead just have that constraint in the original file?
Oh, you put the constraint inside. Yes, it will actually make a difference in terms of computing the probability. So if you put there inside, it will just spit out the marginal probability. Okay, so these are different things. What LPMLN computation will do is it will compute two probabilities. One, actually no. Let me think. So if you put that into the body, you can try. You don't have to guess. My guess is probably is different, but off the top of my head, I cannot be sure. Okay. Okay, so this is the file. So let me actually type in what we just talked about. Okay, so this is one. Let's bring this together. Actually, let's use two. So this is the thing. Oh, we have to query resident. So knowing that Joe is a bird, what is the probability that is a resident bird? So this is 73%. So what Skylar suggests is instead of doing that, let's call this. Oops. So this time, instead of that database, I'm going to call the empty database. I get the same. So maybe same. Okay. Yeah.
So in the evidence file, we added a note of not the constraint we have. But when we add a constraint, it doesn't make something true. Always cancel
Yes.
out the models.
Right.
So I didn't get like how just by writing that line you are saying that it has to be true. Because I didn't see the choice rule which says that it has to be the true.
So the rest of thing is already giving us the whole possibility, right? So think about the main file to generate all possible world. If you put the constraint, you only look at those interpretation that satisfies it.
Yeah, yeah.
So that's the conditioning.
But the main file didn't have any choice.
There's no choice. I don't have to give a choice there. Because that's what the system is already doing inside. Okay, so we'll talk about that maybe next week. Your guessing is right. Choice rule will be actually used internally. But in terms of the input language, you don't need to do. All right, okay, so maybe let me go through the other one. Another thing is this. You can actually feed the ASP rules, ASP program directly. So what you see here is you can view this as LPMLN program with all hard rules, or you can just think about this as typical standard ASP program. Now in standard ASP program, if you give this thing and feed into Klingo, Klingo will say unsatisfiable. However, in LPMLN implementation, you can actually give this option. So to translate all hard rules. So hard rules can be actually violated Okay, that's what we said before. Sometimes we want to forget about the last rule to say that Joe is a resident bird. Okay, or you can forget about the second to the last rule to forget that Joe is a resident bird. If you forget that rule, then everything else becomes consistent. And another option is you forget about this while making all others to be true. Then Joe can be both resident bird and migratory bird at the same time. So actually there are 3 ways to resolve inconsistency here. Okay? If you forget each of the last 3 rules, then you will restore the consistency. So how do we actually utilize this in debugging ASP? So you call this ASP LPMN to ASP with -HR, and this all is actually to give the probability. But if you don't want to know about the probability, you can skip this option. If you do this one, you will actually get this guy. Okay? So there are 3 ways that the thing can be resolved. Okay? So, and in fact, yeah. So each of the case, you can see that one of the last 3 rules are ignored. Okay? So if you put this, then it will show this one. If you put this, it will show the probability. Okay? All right, good. So then, let's actually go to the Bayesian network. So recall Bayesian network. Actually, one of the homework problem too. But I ask you not to use the implementation. Okay? So how do we represent the Bayesian network in LPMLN? So it's actually quite simple. You can encode the conditional probability table in terms of this probability fact. So here you see this one entry, right? Probability of tempering become true. So let's introduce so-called PF atom. This is so-called probabilistic fact. So the tempering become true with 0.02 chance, right? So this thing can be encoded in this line. Okay? And of course, this one will be encoded by this. Let's actually look at this one. So this one is when smoke, when fire is true, what is probability that smoke is true? And that is actually represented by this. Okay? So the convention here that I use, it doesn't have to be this way, but the probability of smoke when fire is true. F1 means fire is true. Probability of smoke is true when fire is false. Okay, that's this probability. Okay, are we together? Okay. So let me actually do one more thing. So this thing can be represented by these 4 lines. This gives me 4 possible combinations. So tempering is true, fire is true, and true, false, false, true, false, false, right? So for each of them, it has a probability. So for each probability is represented by each of these lines. So this is a probability of alarm being true when tempering is true and fire is true. That's a 50-50. And same for the others. Are we together? Is it clear? Okay. All right. So this is actually the part that you encode the table. The next is to encode the graph. And graph encoding is actually simple. It's just a logic rules. So if tempering is true, then probability fact is true, then tempering becomes true. Okay, same as this. Maybe this is easier to see. Alarm can be true depending on these 2, right? Parents. So alarm is true when tempering is true and fire is true. In that case, you have to use the probability fact that tells you that what is probability of alarm being tempering and fire are true. There's also another possibility that alarm can be true when tempering is true but fire is not true. Then you have to use different probability fact, A1, F0. Okay? Same for this. If it's not tempering about fire, then use T0, F1. And if it's not tempering, not fire, then use T0, F0. Okay? And that's all you need to do to encode the Bayesian network. Okay? So I give these specific instructions. So if you didn't follow what I just said, this is actually the formal translation. But I usually find the example is actually good enough. You don't have to look at all this notation. Notation is a bit more complex here. So now let's look at the encoding. In LPMLN to ASP, unlike alchemy, we can actually use log function directly. So this saves your effort to compute. In alchemy, you have to manually compute and feed that negative number inside. But in LPMLN to ASP, you don't have to do. Okay, so that's it. So this is the code. Okay, you just saw in the previous slide. And maybe let me skip this one and let's do something here. Okay, so one thing that we want to do is diagnostic inference. So what is diagnostic inference in Bayesian network? So we are given the effect and we want to find what is the cause, what is the probability of the cause. So for this example, suppose you see that people are leaving, okay? Then can you infer what is the probability of fire is true? Okay, the cause of the fire, what is probability of fire to make people to leave? And if we want to represent this, given the formalization in the previous slide, now we have to give the evidence. The evidence is this one. We observe that people are leaving. Okay, and then you query over the probability of fire. Okay, so let's actually look at this. So fireplace. Okay, so this is the code, and as I said, actually I have named in different database. Okay, so this is just one line. Fire is true. Okay, so let's look at the case. Okay, you can also specify this. I think we can actually skip the output file in LPMLN to ASP. Okay, something is wrong. Bayesian. Oh, okay. Maybe my evidence file is actually wrong. This is actually, sorry. Okay, this should be actually diagnostic query, so it should be not. It should be leaving, not the fire. So let me actually use different thing. So you get the probability of fire to be 0.35. Okay? Next, predictive query. This is actually what I showed. So this is actually opposite. Now you know that fire is happening, then can you infer the probability of people leaving the building? Okay, so you know the cause and you want to predict what will happen as an effect. And doing the same, this is the opposite direction, right? So you're giving that the evidence is now the cause, and you want to find the probability of the effect. Okay, good. You can also mix this inference. So this time, you know that alarm. You know that fire is true, and also leaving is true, and alarm is actually in the middle. Right? What is the probability of alarm to be true? Again, it's the same thing. No matter what kind of inference, different reasoning that you do, the encoding method is the same. You put the basic fire, but the evidence now contains these facts. So fire equals false, meaning that constraint of fire, okay, arrow fire. Leaving equals true is arrow not leaving. And if you do that, you will get probability of alarm to be 93%. There's also intercausal inference, and I think probably okay. Let me just borrow a few minutes here. The intercausal relation is this. I guess everybody who took some AI course knows Bayesian network can do this kind of thing. So let's actually look at this thing. So alarm is caused by tempering and fire, right? Okay. So probability of fire to be true given alarm versus probability of fire equals true given alarm is true and tempering is true. Which one is higher? So if you don't know anything about the tempering and if you only know the alarm is true, okay, then there's a certain chance that fire is true. But now you happen to know the tempering is true, then that explains away the cause for the alarm. So it's less probable that fire is actually true. Okay. So this is actually the output that you do. If you compute without knowing that tempering is true or false, but you know the alarm is true, and if you ask the probability of fire, you will get 36% of chance to be fire. But now, in addition, you know that tempering is true, then the probability of fire goes down because probably it was actually the tempering that caused this alarm. Okay? But if you actually give a different query, now the third time, if fire is true, but alarm equals true and tempering equals false, what do you expect? The very high chance to have the fire. Okay, so let's actually do that as the last thing. So what I have here is this one. So we only know alarm is true. So then you get 36%. Now the second query is, you know that alarm is true, also tempering is true. So if you do this evidence equals to 0.005, the chance to be firing is very low because tempering might be the explanation. But now you give this information, meaning that alarm is true, but tempering was actually false. Then probability of fire is 99%. Okay, so that is explanation. So the fire and tempering are independent cause. But if you know what happens to the effect, then these causes are no longer independent from each other. They actually influence the other things. That's called intercausal inference, or explaining away. And that was the thing. Okay. All right. I think that's it. There's actually another thing about using LPM to MLN, but I'm going to continue next time. Any question? Okay, so let's stop here.